Hello everyone and welcome back to the Victoria Game Engine series. Today we're going to be focusing on atomic counters and refcounts. So you may be asking yourself the question, what is an atomic counter? Put simply, an atomic counter is a variable of atomic data, so floats, ints, chars, that kind of thing, that is incremented and decremented over time. The reason that this is going to differ from just using a variable that we add and delete numbers to is that first off, it's going to be using the thread safe version of this operation, which is a part of the C standard library that we'll be using that does all of this in a thread safe manner. And secondly, it will also be our system that we use for our ref counts. Now, ref counts stand for reference counts. So they are a counter that can be incremented and decremented to a certain amount and allow us to control when data should and shouldn't be freed and what actions should go on when we are freeing that data. For example, in our current implementation of our vector class, whenever a pointer is shared between two different data types, when that data that is being shared is freed, one of the vectors will still try to read from that freed data and will run into problems because, of course, the data has been shared and it is not unique to that individual vector. When we implement a ref count into the vector class, it will allow us to control when the pointer that contains that initial memory allocation is actually freed, and therefore at what point we can destroy the data and therefore free up more memory in our system. So with that all out of the way, let's go straight into writing some of the code for this. The first file we're going to be creating is the atomiccounter.h header file, and that's going to exist in our data folder. So up here, we're going to click on new file. We're going to call it atomiccounter.h. And within here, we're going to pragma once. We're going to include the type defs because we're going to be needing some of those. And we're also going to include atomic, which is the C++ atomic library, which we will be using in a moment. Now, the class itself is going to be a template class because we're going to want to specify what kind of data we're keeping in here. std atomic can use multiple different atomic data types. It can't use complex data types, but it can use basic data types like ints and floats, as I said earlier. We're mostly going to be using it with 64-bit integers, but there may be some cases where we use it with other numbers. That being said, we're going to call template type name t. I'm going to create a class of atomic counter. Within this class, we're going to have a variable called std atomic of type t, and we're going to call this the counter. And beyond that, we have the rest of the class, which I'll explain in further detail. Starting up at the top here, we have some fairly basic variables. Of course, we have our getter and setter. These, of course, load the data that's currently in memory and also set the value to whatever we want it to be. In most cases, get and set will not be used. Get is more likely to be used. Set is not used very often. Here we have add and subtract functions. So these will just add a value to the value we have, and the same thing down here. Also note the memory order here. So this simply refers to how the memory is being loaded. So in the case of memory order acquire, we just want to acquire the value. Here we want to release the previously held value, and so on and so forth. So we kind of have a very similar thing here with increments. So this just adds 1 to the counter, and it calls to fetch add, which will acquire the data and then release the old one. But here you'll notice that we add 1 to the counter and then we add here. What this is doing is normally the counter will increment the value but return the previously held value, which is what it does here. But in this case, we don't want to do that. We want to just get the current value. So increment will just return that value. So we can add 1. And a similar thing here. This hasn't been implemented in add and sub, so this may change in the future, but for now, this is how the implementation is. And then down here, we have conditional increment. A conditional increment will only increase the counter if it is greater than 0 or if C is somehow greater than C+1. In almost every circumstance, I understand, this should be the case. But sometimes, so for example, say you have two separate threads operating on the same ref counted item. If they try to do two separate memory accesses to the same object, that's going to cause some problems. So what we do instead is we say, okay, well, if the value's already bigger than that and we're trying to increment it by 1, then we need to keep incrementing it until it is bigger than 1. So this is what this does. It effectively looks to load to see if that value has changed at some point, because there is a chance that during the processing between this call here and then this next CPU cycle, a separate thread may have changed that value in memory. And otherwise it will continue as is. A very similar thing here for exchange of greater. So if the current value you have is less than the value that we've input, then we set it, and opposite for exchange of lesser. And lastly, we have atomic counter. This is just the constructor. All this will do is take initialization value and whatever value you want to set it to. And that's pretty much all it does. Next up, we have the Refcount class. This is going to be effectively a wrapper on the atomic counter, and it's going to have just slightly different names for the functions it does. So below here, we're going to call class Refcount. Within here, we're going to have only one variable. This is an atomic counter holding a type uint64. And this is our refc. And there's not a lot else there on the private side, since all we want to do is wrap the atomic counter. So then here, I'll just give you the functions and I'll explain them 3 from the top. So the first function we have up here is ref. All ref does is let you know if the ref count was incremented successfully. The ref count will be successful if the value is not 0. Then there's refval, which will just return the value that you get when you increment the ref count. Then we have unref. This will just see if decrementing the ref count is equal to 0. So if it is equal to 0, then it returns true. Otherwise, the ref count has not been resolved to 0. And we also have unrefval, which is the same as refval, but for when we're decrementing. So set allows us to reset the value to a given amount. It doesn't necessarily reset entirety, but in most cases, you'll probably be using it to reset the ref count back to 1. Get does pretty much what it says, just returns the current ref count. And init is what we use whenever we are setting up a ref count, in which it will set the value to whatever it does. Now, do note here, ref counts do not have a constructor or a destructor. They are created, they're initialized, they are decremented and incremented. They are never constructed and destructed because that is done more or less on the fly. So std atomic will construct and destruct itself as it sees fit. Now, with all of that out of the way, we can then go into some of our current classes and implement these properly to give some better functionality. All right, so the main class that's going to benefit from this is the only class we already have set up, and that is our vector class. Within here, we have a couple of things that we could really do with changing anyway. So we're going to go and do those in this video, as well as do a couple of other changes. So first things first, we're actually going to get rid of this 8 width variable data size. Reason being that the vector class itself, by default, is already something pretty big. With this, the uint8 does not take up 8 bits. It takes up 8 bytes because 7 of those are excess because the compiler does a little bit of optimization under the hood. And for our sake, it's probably not best that the data size is kept, since we can just query it using our preprocessor part of size of. So we're just going to get rid of that for now. Up here, we're going to declare a friend class, and that's going to be our friend class string. String doesn't have to be defined at this point. You just have to know that it is a class that exists. Whenever the string class is used, it can now access private functions of the vector template, which we will be showing why that is important later. And before I'm a total idiot, we do actually have to include something. So up here, we're going to include from our data, we're going to include atomic counter. And then here, we're going to create our ref counts. You may be sitting there wondering why on earth we got rid of an 8-byte value only to add another 8-byte value, because ref count is actually 8 bytes. Reason being behind this is that the size of is a lot easier to implement than something like this, and you also can't have both of them because the ref count will take up 8 bytes, the uint8 will take up 8 bytes, and then if we want to have any kind of interoperability between our string class specifically and the variant, that simply won't exist because the template will be too big for any of that to happen. Another thing that we're going to change is we're going to be moving our functions here. So our ref, unref, and resize are all going to be moved to being private. The only place that these were really being used was some of our string stuff. So we will be saying goodbye to those, and we're going to move them up into the private part here. And in fact, we're also going to be adding a couple of extra functions to this. The function that we're first going to be adding is called copy on write. I'll explain what a copy on write is when we get there. And we're also going to create another function called realloc. So error underscore realloc. Uint 64 and size. This is primarily going to be a helper function that's just going to allocate data whenever it's called, to save a couple of times that we will occasionally call functions where we need to reallocate several times during a function. And it's simply easier for us to reallocate if we have a dedicated function. We are actually going to be changing something here in our set function. That is, we're going to be adding a call to copy on write, which will make a lot more sense when I actually get to that function. We also have another function a little bit further down, a couple of functions actually that we'll want to create. And I'll just put them in here because they do come with a little bit of documentation. So this is our get ref count and resize function. As you can imagine, all get ref count does is simply returns the current ref count object that we have applied to this class. And what resize does is a public facing version of the old resize function. And the reason behind this is that sometimes you'll want to resize the vector class to have a number of elements rather than a number of bytes. So what we do in this case is that we just pass the new size times the size of t. And that's really all that class needs to do. But there are more changes coming up. So let's head down to our ref function. This function is going to change quite extensively. So within here, we're going to do a couple extra changes to variables that we have. So we're going to actually set p size to be 0, and we're also going to set p element count to be 0, because we want to make sure that both of those are explicitly clear. And sometimes when you're using data, the constructor for the vector class sometimes isn't called when you're using allocations. And as a result, the data is totally messed up when you do a ref. So in this case, we want to make sure that p size and p element count are actually zeroed out anyway, so they don't hold garbage data. The next thing that we're also going to do here is we're going to increment the other ref count. So we're going to call to if p from the vector that we're copying this from, that will also have a ref count, .get ref count .get. And if that value is greater than 0, then we'll want to increment its ref count. So p from .get ref count .ref. This may not necessarily be needed, so I may test this and remove it in a refactoring video if need be. But for now, we'll keep it here because, as is general knowledge with code, you should never touch something if it doesn't break it. Now down to our unref. If you're like me and you've actually used this vector class a whole bunch across your code, this is a change you're going to like. Because of ref counts, the primary reason that we actually made ref counts in this video is because of something that I want to do with our basic objects that we're going to be dealing with in the next video. But one of the main reasons I did this video is because the stuff that we're about to do here is very useful for making this vector class a lot more idiot-proof. And by idiot-proof, I mean that it won't have accidental double freeze, and I'm going to explain that now. So here we're going to call to our ref count, and we're going to call to unrefval. This will, of course, do an unref, but it will also return the value that it has. And if that value is greater than 0, at this point, it means that the ref count for our current object, our vector class, the data that it currently holds is being used elsewhere. And it's a direct copy, which means it's effectively the same pointer. So in this case, we do actually need to clear out that data, set everything to null, but we don't want to free it itself because it's still in use elsewhere in our application. So instead, we're just going to set the current pointer to be null pointer so that it can't be read from, and we're going to return. So the next function we're actually going to throw in here is our copy on write function. This is, of course, completely new and is going to serve a couple of interesting purposes. So first things first, what is a copy on write? So copy on write is a kind of data type that you'll often deal with. Copy on write data is where whenever the memory is being written to in such a way so that there are two separate instances of the same array that share the same pointer, but you want them to still be unique because, of course, two separate instances may be used in different ways if you're changing the data that's held by them. You need a way to make sure that they are distinct. And the way we do this is through copy on write, where every time you write to the array, just before you're about to write any data to it, you copy it to an entirely new block of memory. And the old block of memory can be used by the old one until that runs out of scope and effectively is freed. And this one will do the same thing. So the function itself here, as we see, all it checks is if the ref count is greater than 1. If it's equal to 1 or if it's less than 1, we don't really care about copying the data because either it's already unique in the first place, so there's no other type it's sharing with, in which case continue on. And if there's nothing in it, then of course we don't want to copy nothing, so we don't do anything there. But if there's more than one instance of effectively the same memory block, then we want to start writing to new ones. And that is what we do here. So what it does is it first calls to our static allocator to allocate a new block that is of p size, which is the current size of the array. That will fail if, of course, we run out of memory, in which case it will return a null pointer, and we cry and throw a hissy fit about that here. But of course, that's a pretty serious thing to happen. So of course, we're going to throw an error about it. We then check to see if the data is, of course, trivially copyable, in which case we need to use the placement new operator, which will just place it in the new data array from our old data array. And otherwise, it can just be directly copied from that data. Then we call to unref to free up all of the data that currently exists. Of course, if that's also being used, which it almost certainly is in this case, then we're just going to set the pointer to null pointer and return, like we did up here. We're then going to set the pointer to be the new data, and we're going to set the ref count to be equal to 1, because at this point, it is now unique, and it can be written to how we want. Now, something I almost forgot to do during this video was that our data size no longer exists. So this thing here, we need to go through and basically see wherever it's used and get rid of it. So for instance, here, the vector constructor can now just be empty. It doesn't need to do anything. We go right to the top. The first time, it doesn't really need to be copied across because we're just using size of now. Same thing here. And you kind of see where this is going. It's just getting rid of wherever it is used. Or at least where it needs to be. So like here, we'll replace it with size of t. Because that's an operation that the compiler can do in compiling. So it can just replace that with a number when needed. Same kind of thing here. Just replace it with a size of t instead. And again. And you'll kind of see where this pattern is going. Don't really need to do the insert out there because, of course, we can just use the size of t. And there's a lot of these individual operations that we can now trim down because of this. In hindsight, probably was a stupid thing to do because it can just be fixed in like 10 seconds by just calling to size of t. I don't know why I did it, but that has changed now. On to slightly more interesting things. We're going to be changing a lot about our resize function. First and foremost, we are going to be checking that our p size is 0 and our p element count is 0. Again, this is just me being pedantic about making sure that these are definitely 0 if we are allocating an array of vectors, for instance. We are also almost always going to be copying the data over, so we are going to call a preemptive copy on write before anything else in the function happens. Before we even check if we're removing data or adding data, we are just copying everything to a new block because we know almost for certain at this point that there is going to be more than one case of the data being shared. So within the first check here, as I mentioned earlier about the new realloc function, so here we're going to change the data ever so slightly. Before we do that, there's just one tiny thing to add here. We're going to set the ref count to 1 here. Because at this point, if the current size is 0, it's normally because the array is brand new. The copy on write probably won't even trigger. It'll be, the ref counts could be set to 0 for all we know. So we're just going to set it to 1 preemptively. And then all of this can kind of get rid, and we can instead get an error. And it's going to be equal to realloc of the new size. And if there is an error, so remember in the error enum that we created, OK is 0. So if error is greater than 0, then something's gone wrong in our subsystem. So let's return a value. So we return error here, and that'll just let us know what went wrong. And otherwise, this function here stays mostly the same. The only thing that does change is that we get the same error call here, where we call to realloc the new size, and the same kind of checking for errors here as well. And otherwise, we can do everything as usual, and the function kind of stays mostly the same. On to that realloc function. So it's a very simple function. I'll explain it here. That should just be a uint, sorry. Yeah. The actual data type I use, I moved to u64 instead of uint64. We might do that in a future episode, but see how it goes. So all realloc does here is it just calls to reallocate, as you would imagine, on our current pointer. And then sets the ref count to 1, because of course at this point, pointer that we've assigned it to is now totally unique. So we don't need to worry about doing like copy on write here. It's just reallocating the current pointer. So that's what we do. And again, we just set it to 1. Pointer is the new data, and we return all good from there. And doing a quick scan in the class lets me know that this should now be more or less entirely rewritten to support our new subsystems. All right, so with this out of the way, we can just go here. We're going to clean the binaries first, because there is a case that it might throw some errors with the new atomic counter being involved. So that should just get rid of bin for us. And we can hit Control-Shift-B, rebuild the entire project. Oh, it is a problem. Oh, yeah, okay. Again, this is just because things are named slightly differently across my projects. Some of the refactoring I've done on later versions of this have meant that like names, so it wasn't memory, it's static allocator at the moment. We might change that, of course, but that is all good now. So if we hit Control-Shift-B again. Oh, right. Oh, yeah. Okay, so we pass P size here. Yeah. Again, just problems with the old systems I have. So that should compile now. Oh. Yes. Okay, I remember exactly what this is. Right. Okay, so the error we have here is a really annoying error that you end up getting during linking sometimes on Windows. So for some reason, when you're building for a debug build, Windows doesn't like it when you don't have certain libraries included, specifically for MSVC, so the Microsoft compiler. What that means is that we just need to add a couple of linker flags here. So in our debug build, we are just going to add these 3 lines here, or these 3 flags here. This will just link us to the MSVC runtime, the VC runtime, and the Universal C runtime. And all of those are the debug versions of those libraries. Reason we're doing it this way is because in short, Windows is dumb and insists on these because of their C runtime debug report. So just a way for the compiler to know when allocations and being valid versus invalid pointers can be checked in debug builds. So you have to add those because otherwise it doesn't link properly. You do get this warning now every now and then when you do the building this way. It'll just tell you that default libcmt conflicts with the use of the other libraries, use/no default lib library. You can just ignore that. It doesn't really mean anything, at least not to my knowledge. And from there, you can hit F5 and the project should hopefully run. And there we go. Nothing really has changed. We're using very limited numbers of strings, so you won't see as many benefits from using this. But when we go to use other classes, we will be able to do things that we previously couldn't do, and that will make our lives a lot easier. All right, and that's pretty much this video done. So in the next video, I think our plan is that we're going to start moving on to some of the base objects that are going to be making up our scenes. So this will be the system that makes up our nodes, so our physical world objects, our tree structures, resources, all of those things will be using these atomic counters that we've created. And we need to do that scaffolding so that we can start moving towards having a bit more structure for when we get to our rendering stuff that we'll be doing later down the line. Of course, there's a couple other things, other systems that will be going in place over that time before we move on to actually focusing a bit more on rendering, but those will come when we need to. So anyway, thank you very much for watching this video. I'll see you in the next one, and a bye.